Hello, we're Group 6 and we're designing lightweight siege weapons. My name's Tiffany.
I'm Ahmed.
I'm Savannah.
And my name is Spencer.
So, our good king wishes to aggressively expand his kingdom. We were commissioned by our good king to design a catapult fit for sieging the neighboring rival city. Our spies have obtained critical information. The neighboring king and his citizens are allergic to watermelons. As such, this lightweight trebuchet will be fit to rain devastating blows of watermelon upon the neighboring city.
This project aims to first analyze the forces experienced by the trebuchet under firing load, and then use that analysis to design a minimum weight trebuchet while taking into account failure criterions such as deflection, yielding, and buckling. Our siege weapon of choice, the trebuchet, will be comprised of three main components: the trebuchet arm, the pin at which the arm rotates about, as well as its supporting truss. All of these components can be seen on the diagram within the slide, where the trebuchet arm will be loaded by both the watermelon as well as counterweight. A trebuchet is one of many types of war machines used to essentially launch heavy projectiles at enemies and their strongholds. In principle, it functions by using the energy of a falling counterweight to sling a projectile, using mechanical advantage to achieve a high launch speed. As the main arm rotates clockwise due to the falling counterweight, the payload will experience a strong centripetal acceleration, and that will cause it to move outwards and eventually away from the sling towards the target. Because of how the trebuchet functions, the heavier the counterweight is relative to the payload, the faster and farther the payload will travel. However, increasing the mass of the counterweight beyond a certain point will not be helpful to us, as the limiting speed of the falling counterweight is its terminal velocity. Because of these physics principles, the trebuchet boasts a greater range capacity as well as greater accuracy than other siege engines of the past. Research has guided us to designing our loading such that the optimal weight ratio between counterweight and the watermelon is 133:1. We will be basing our design calculations around initial factors such as the weight of the typical watermelon and the corresponding counterweight for the system. And we have estimated the weight of a watermelon to be roughly 10 kilograms, and therefore an optimal counterweight for that watermelon will be just under 1,400 kilograms.
For the components of our trebuchet, we have the materials and their properties listed in the chart displayed in the slide, including compression strength, tensile strength, elastic modulus, and rupture modulus. We are using a 2024 aluminum material for the rotating rod and Sitka spruce wood for the trebuchet arm and truss members.
We began with the structural analysis of the catapult arm, which will hold a watermelon on one end and a counterweight on the other end. And in center-ish area, it will be supported by a rotating rod. Under maximum static loading, as shown in this visual, the watermelon end will also have a rope to hold down the trebuchet prior to launch. Due to this angular condition, we analyzed the stresses this arm will experience in bending and in tension with the equations shown. Using these stress equations, we compared the necessary dimensions and chose the larger of the two.
For the analysis of the rolling pin, we use the max yield stress of the material with a given safety factor in order to size the radius of the pin. Then using the elastic modulus, we can find the max deflection of the beam to see if it falls within our predefined range. For these calculations, we use the beam bending equation with supports on both ends and a single load in the center. The load contains the weight of the payload, the counterweight, and the weight of the swinging arm beam. For the rolling pin, we use metal instead of wood as there would be less friction as the metal rod spins, and when nearing failure criteria, the wood will crack, decreasing the structural integrity of the pin, while metal will deform elastically before total failure.
Our structural analysis for the supporting truss consisted of measuring the forces generated in each member due to the weight of the rolling pin, catapulting arm, and counterweight projectile weights. Members 1-3 and 2-3 were in compression, so the yield stress and buckling failure were considered in calculating the minimum cross-sectional area. For member 1-2, only yield stress was required as the member was in tension. The formulas used for this analysis are written above. For failure criteria, we used a safety factor of 2 when calculating for the required minimum masses and areas of our components. The catapulting arm required analyzing the max yield stress of our material while using 2 times the average weight of a watermelon. For the rolling pin, we measured the max deflection and bending of our component with a safety factor of 2. Measuring the max bending stress, we were able to analyze the minimum radius required. We then calculated the max deflection that occurs to ensure it would not result in failure depending on our material type. For our truss structure, we again analyzed the max yield stress for the one member in tension, while the 2 slanted members required analyzing the max compression strength and buckling with a safety factor of 2. In order to achieve minimum mass, we calculated the cross-sections required of each component with respective material types in mind. We chose what material types were best under each loading and conditions. Due to Sitka spruce's great strength to weight ratio and high modulus of elasticity, it was a perfect choice for our catapult arm and truss structure. We were initially going to use 304 stainless steel for the rolling pin due to its incredibly high elastic modulus, but we ended up instead choosing 2024 aluminum for our rolling pin for its high compression and tensile strength capabilities as a metal and its resistance to bending and deflection, while being more lightweight than steel. 2024 aluminum was a better fit for our purposes as it provided the required strength while reducing the mass of our structure as much as possible.
Displayed here are the specifications of our catapult. As seen, the catapult arm contains the largest cross-sectional area, which is sensible since it's the longest and will be supporting the massive counterweight. Members 1-3 and 2-3, which are the slanted members of our triangular support truss, have a cross-sectional area that is larger than the horizontal member. This also makes sense as they are supporting compressive loads of the catapult that are transferred from the rotating rod.
In conclusion, our engineered trebuchet will be able to effectively rain down watermelons of mass destruction while maintaining structural stability. Additionally, careful consideration and choice of our material options allowed us to optimize our design for minimum weight, high strength, as well as high functionality. Throughout the process of designing our siege weapon, we have ensured that all of our trebuchet components will be able to withstand all potential stresses, while also taking into account for failure due to yielding, buckling, and deflection.
And finally, thank you so much for your time and attention.